In this lesson, we'll talk about recursion with Java. Now, recursion is a programming technique that is a natural fit for certain kinds of problems. These are problems where writing a loop might be less of a fit. So an example is searching for a file in a folder hierarchy, right? To use recursion, in such cases, you would define a recursive method. This is a method that would call itself. So let's take an example. The example that's typically used here is the mathematical function factorial. And if you recall from your math class, factorial is defined like this. N factorial. Factorial of n is written with an exclamation mark, right? So if n is 0, the value of n factorial is 1. If n is greater than 0, then the value of n factorial is defined as n times n minus 1 factorial. So you can see the recursion here with using factorial to define factorial, right? So let's actually write code for factorial. So here, implementing something recursively, you have to think about two things. The first is a stopping condition. So it's a condition where you would make no more recursive calls and you simply return a value. And the second is obviously the recursive call, but here the key idea is that when you call something recursively, it has to be a subproblem which is smaller than the original problem. So the recursive method keeps on calling itself with a smaller and smaller set of problems till it reaches the stopping condition and there's no more recursive calls, and it actually returns a value which is propagated back up, right, through the call stack. So let's go ahead and look at code for recursion. So this is the code for recursion. We have our main class and the main method, and we have defined a method for factorial. So our main method, all it does, it prompts for a positive number, reads it, and calls factorial on that number n and prints its value. Now the factorial method here is very simple. It has a stopping condition, so where n is equal to 0, it returns 1, and where otherwise it will return n times and calls factorial recursively, but on a smaller problem space. So let's actually run this and see how it would work. So we copy this. We'd fire up IntelliJ and paste it here and then just run it. So you'll see we can put in 10 and it prints out the value, all the while using recursion, right? So let's go back. And this is the example that I just showed. The great thing about our implementation is if you look at this definition here, it looks identical to the mathematical definition. So factorial is very naturally specified using recursion. We have talked about how we make recursive calls, so let's look at it visually. So what exactly is happening here? So let's take the example where we call factorial with 4. So in this case, it makes a recursive call and it returns 4 times factorial 3, which again returns 3 times factorial 2, and it keeps going down till you get to the stopping condition, which is factorial 0, which returns 1. And now the function calls that have been, or the method calls that have been made are now returning and popping back up. So now this returns 1, and then the result is returned to the previous call, and it keeps popping up till it comes up here, and then the result is computed, and the final value being 24, right? So here's a question. What if we had just simply not had the stopping condition, right? And just called this, right? And the answer is what you would get is the calls would never stop. So it would keep on calling factorial with smaller and smaller values. It'll get up to 0 and blow right past it into negative space and keep on going. And what you would get is what's called infinite recursion. You might have heard of infinite iteration or infinite loop, and where it doesn't stop. Here you get infinite recursion. Now, the question is, what happens if you actually try this? And let's just actually try this and see what Java does when you're running this. So what we'll do is we'll replace this call, this definition with actually we'll take this one too, okay, with this definition with this one, which will give us infinite iteration. So let's run this and see what happens, right? And of course, let's just put the same value, and you get an error. So let's see what is happening here. So you can see the program is calling itself over and over again till the runtime system determines that no, this is never ever going to stop, and gives you an exception called stack overflow. That's the exception you get when you have infinite iteration. So this is what I mentioned right here. Now, why is it called stack overflow? Where's the stack, and and where's the overflow coming from? And this has to do with how methods are handled by the runtime system. Every time there is a method call, Java creates an activation record for that method call on the memory, and it uses kind of a stack methodology. Within the activation record, it keeps values of local variables to preserve it when the call is returned. Now, if that method calls another method, there's another activation record that's created on top. So let's look at visually what this might look like. So for the above factorial 4 example, you've made a method call, which again calls factorial 3. So when that's called, another activation record is created, and then yet another till you get to 0. And now this call starts, is the stopping condition. It starts returning values, and now it starts popping the activation records off the stack, and till you reach the final activation record, which returns the value. And the reason why it's called stack overflow is that if there's infinite iteration, it'll keep on putting things on the stack, and you will get an overflow and will not stop, and the runtime will detect that and give you a stack overflow exception. Now, another example that we use often to demonstrate recursion is calculating the Fibonacci series. It's a well-known mathematical series. Fibonacci is defined as follows. It's got two stopping conditions. Index passed in is 0, then the value is 0. If it's 1, then the value is 1. For everything else, for indices that are greater than 1, it is Fibonacci of index minus 1 plus Fibonacci of index minus 2, right? So you can kind of see the series here. These are the two first ones that you get, index 0 and index 1. Then the next one is an addition of the last two, right? Which is 1. And then the next one is the addition of the last two, which is 2. And then you kind of go on. Any one particular one, like 34, is the sum of the last two. And that's how Fibonacci is calculated. As I said, the stopping condition is 1 or 0. So the interesting thing here, different from factorial, is that there are two recursive calls now, right? And each recursive call is in fact reducing the space, and it's reducing this problem space by each one is by a little bit, right? So let's actually see what this might look like in code. And as you can imagine, it looks very much like the definition. Same thing, we're reading an index and calling this method Fibonacci. And here you'll see if it's either index is 0 or index is 1, you just return the value, and otherwise the value is Fibonacci of index minus 1 and index minus 2. Okay, so let's run this, and let's copy and run. And this has some interesting performance implications, which we will get to. So let's close this, and we'll replace our implementation with Fibonacci, which we have done, and let's run it. So let's just choose 7. It gives 13, and you will see if you kind of went back here, 7, so 0, 1, 2, 3, 4, 5, 6, and 7, and 8, 9, 10, 11. So let's try 11. It should give us 84. Let's run it again, if I'm right. 89, sorry, not 84. And that's what you get. Okay, so that's what I've said. Now let's see what is happening here in terms of recursion. So let's take a small example. We will say Fibonacci of 4. Now Fibonacci of 4 is calculated by Fibonacci of 3 plus Fibonacci of 2. This creates two different recursion. So there's a Fibonacci of 2, which is Fibonacci of 1, Fibonacci of 0, and then kind of gets to the stopping condition and pops back up. And here it goes on till it pops back up, right? Now, do you see a problem here, right? And the problem is that there are lots of duplicated calls. You can see Fibonacci 1 here, Fibonacci 1 here, Fibonacci 2 being called here, Fibonacci 2 being called here. So there's a lot of repeated computation going on. In fact, Fibonacci 2 is called twice, Fibonacci 1 is called 3 times, and so on. So you can imagine if you're doing Fibonacci of 10, there's a lot of duplication. Right. So actually, we can see how much duplication there is, or how many recursive calls there are, by just instrumenting it a little bit. So we'll replace our implementation is by just every time Fibonacci is called, we keep a counter, right? And we have a static value here that keeps the counts, and we print it at the end is the only changes I've made. So I'm going to do this. Right, and then we'll try this out. So here we will just copy this and place this, right? So now it's measuring the recursive calls. So let's try this out, right? So if suppose we do 5, you can see there are 15 calls, and let's kind of go on. We said 10. You will start seeing it grow at 177 calls. Let's do 20, and now you're suddenly getting almost 22,000 calls just from going from that. And let's just try 30. Now you've got 2 million calls, right? Just quite a lot of growth. Let's try 40. And you got, what do you got? 331 million calls. And then let's try 50 and see what happens. And now here you have to get ready to wait a little bit. So it's running, and that's kind of what I talk about here in this lesson, is that you will see that there is very steep growth, right? So the final call 50 is really 40 billion recursive calls, right? So can become recursion can get very, very inefficient if you are not careful, right? So it is not, you don't use it for efficiency, you use it for simplicity of coding it up. Actually, let's go back and see whether that thing returned. No, it's still running. So, oh, there it just returned. So, okay. So now let's just talk about recursion and what it means to think recursively, right? So recursion, is everywhere. This picture might remind you of the movie Inception, where, where they're dreaming and they go from dream within a dream within a dream. And there is a famous image of a Dutch cocoa brand that represented recursion. There is the person modeling here is actually holding a box which has the same picture, and so it's recursively. And this actually is called the Droste effect, and it refers to the artistic effect of an image recursively appearing within itself. So this is at a museum. The person's looking at a picture of the same thing, and actually you can do a Google search of it, and you'll see lots of interesting examples of these things happening, right? So recursion generally always has the following properties. You have some if-else conditional or switch statements with different cases, right? And one or more of those cases are stopping conditions. They have to be. And they are recursive calls that will reduce the original problem into smaller spaces, and you get closer and closer to the stopping condition, and then you start popping back up, right? So you use recursion to, it's very easy way to think about certain problems recursively, right? And that's what I'm talking about here. There are actually whole programming languages that are based on recursion. Lisp is a programming language still in use today that it is very much depends on recursion, its original form, right? Another example of a problem that's very easy to solve with recursion is detecting whether something is a palindrome. And a palindrome is something that is read same backwards and forwards, like race car or kayak or madam. You know, they are same backwards and forwards. And actually, you can have multi-word palindromes like my gym and was it a cat I saw? If you read it backwards, these are all exactly the same, right? So how do you check if a string is a palindrome? You know, this is very easy to think about, right? So essentially what you would do, the way you would solve it is you would look at the first character and the last character of the string and compare. They're the same. If they're the same, then you recursively keep going down. What are the stopping conditions? The stopping conditions are if the string is empty, you've gotten to or is only left with one character, right? If it's an odd number of characters, or that one of the two characters from the beginning are not the same, right? So those are the stopping conditions. And this is we won't really type it up, but this is the code for checking palindrome. This is exactly what I talked about here. The stopping condition is if you're down to an empty string or one character. That means, yeah, it is a palindrome. Or if the two characters are not the same, then this never was a palindrome. Otherwise, you recurse on a smaller string, right? Now, you are already used to using loops. So in loops, when you're defining loops, you provide a loop body, and the repetition of the loop body is controlled by the structure of the loop, right? So it could be a while loop where you have a Boolean condition. It could be a for loop where you have counters and increments and an end condition check, right? In recursion, the method itself, it calls itself recursively, right? And a selection statement such as if, else, or switch is used to control whether the method calls itself recursively or not. Now, recursion, this is very important. Recursion has significant overhead. Every time you call the method, system allocates memory, an activation record for all the local variables and parameters, right? And if you keep on doing that, it's consuming memory and time, right? The key thing to note is that any problem that can be solved recursively can also be rewritten, can be coded iteratively with loops, right? For example, factorial can be rewritten using iteration with loops as follows, right? And you can have a stopping condition, and then you just have a for loop to multiply the numbers, right? So then the question is then, why do you want to use iteration at all? And there are cases where it would be better to use recursion. And that's specifically if the problem space is small and performance is not really a consideration. So a folder hierarchy is typically small, so it's very usable for that, and performance is not a factor. And then certain problems, like solving this classical problem, Towers of Hanoi, it is very difficult to think about unless you're using recursion. So it's for our brains, it's very easy to think about recursively, but it's much harder otherwise, right? I do want to talk about a special kind of recursion called tail recursion, right? A method is tail recursive if no more work is done on returning after the recursive call. So a tail recursive method would look like this, that you have a bunch of code, your stopping condition, whatever, and the very last thing you do is you call the the method itself recursively, and there's no other work being done. This one is not tail recursive because you call it recursively and then you do some work afterwards, right? So, for example, is palindrome is tail recursive because no work is done afterwards. If you kind of go back here, it just returns, right after that. There's no calculation being done afterwards. Now, factorial and Fibonacci are here. Let's just look at factorial and see, is that really tail recursive, right? It is called, recursive call is made at the end, but then you do a little bit of work here to multiply the values. So this is, the factorial is not tail recursive, right? So you have an example of tail recursion and not tail recursion. Let's go back to that section. Now, tail recursion is a desirable thing because you don't need to store intermediate calls on the stack, and compilers can reduce the stack size, memory usage by detecting such conditions. Also, the very last thing to note is that non-tail recursive methods can sometimes be converted into tail recursive by using extra parameters, right? And here I have, there's another version of factorial I've created where I am keeping the result in an additional parameter, and by using this, I have kind of eliminated the need to have a n multiplied here, right? So this version is tail recursive. Now, suppose you still wanted your original signature where you didn't have this extra parameter, you could always use overloading and define another factorial which actually does the work of passing this in the extra parameter in for you, right? So there are ways around recursion to optimize things. All right, so this has been a lesson on recursion, a very interesting topic.